In the 1700s, a scientist called Charles Augustin de Coulomb, forgive my French accent, studied charge, and he discovered that there was a law which could be used to describe the force between two charges. And unsurprisingly, we know this as Coulombs Law, and it describes the force, so the force that is between two charges Q1 and Q2 is proportional to the size of those two charges. So as Q1 or Q2 goes up, then the force will also go up. It is also inversely proportional to the square of the distance between those two charges. And it has a constant out the front which is known as K, and K is equal to a value of 8.99 by 10 to the 9 newtons meters squared per coulomb squared. And you can work that out from looking at the units of each of these values here. And this is called the Coulomb constant. So basically what this is saying is that as Q1 or Q2 go up, force also goes up. But equally, if the distance between them gets larger, then the force will get smaller quite rapidly, because there's an inverse square law, so it actually drops off quite quickly. Sorry, we've lost the outline there. So that's Coulomb's law. We can also write it another way, which I've shown here. This is exactly the same law. We still have that the force is proportional to each of those charges and inversely proportional to the distance between them. But instead of the K, we've replaced it with this here. Now this value here is called the permittivity of free space. And in a vacuum, it has a value which I'll write here. And of course, if we were in a material other than in a vacuum, we would use a different value there. So here is just a simple example using Coulomb's law, and we're asked to find the force between two electrons, which are negatively charged, located at 1 centimetre apart. So we can start this by saying, well, we know the distance between them has a distance r of, what is it, 1 centimetre, 1.0 centimetres. And we can rewrite that as 1.0 by 10 to the minus 2 metres. It's always good to put these things in SI units. The charge on the first charge, it's 1 electron, so it's 1 unit elementary charge unit, which equals in coulombs 1.60 by 10 to the minus 19 coulombs. And Q2 will be exactly the same. It'll be 1.6 by 10 to the minus 19 coulombs. We're just going to use the first of those laws where our force is equal to a constant K times Q1, Q2 on R squared. Again, just reminding you that as the Q's go up, the force goes up. As the R goes up, the force goes down. And if we substitute in those values there, we get that convoluted expression there, which turns out to be, whoop, here's our solution, yes, we're halfway there, 2.30 by 10 to the minus 24 newtons. Doesn't sound like a lot. Now I've not been very careful here. I should be putting in here, the negatives in the Q's. And of course, negative times a negative will still give me a positive value. And you know, because they are electrons, it will be a repulsion. So I'm just going to write that there, repulsion, or away from each other. And you'll find that always a positive value of F means repulsion. Next, we're just going to take Coulomb's law one small step further, and just to talk briefly about situations when the charge is not at just a point charge, not just a point charge, like a very, very small area of charge. So often we talk about charge as being just a very small point of charge, and it's easy to deal with mathematically, but also sometimes we have charge which is distributed over an area, and when we get into integral calculus at university level physics, you'll be able to analyse these in much more detail. But it turns out if you do the calculus on a sphere of charge or a shell of charge, like this large one here, it turns out that the charge acts as if all of the charge were at the centre of that sphere. So there's the charge acting all in the centre of the sphere there, and it's almost as if you had a charge of size large Q, but just in a point right in the middle there. Not a very nice point, but there you go. So just to recap, a spherically symmetric sphere or shell of charge acts as if all the charge were at the centre of the sphere, and so in calculations like Coulombs law, we use the distance between the centre of the charges as the value of r that we're interested in those calculations. So we pretend that it's just a point charge.